In this video, we're going to look at the mechanism for the enzyme chymotrypsin. And so our goal is really to understand that mechanism and talk about the chemistry that occurs at that active site with the triad of serine, histidine, and aspartate residues. And real quickly, I want to first talk just a little bit about some kind of common catalytic strategies that are used by many enzymes. So covalent catalysis, where we see that the active site contains a nucleophile that is briefly forms this covalent bond. So it can forming a covalent bond, covalent catalysis. General acid-base catalysis, that's when we have some molecule other than water that's donating or accepting a proton. Metal ion catalysis, so metal ions can function in many ways, and we'll look at a couple of examples of that in some future videos. And catalysis by essentially orientation. So the enzyme brings the substrates together to get them close enough together and in the right orientation to react. So if we talk about chymotrypsin and picture this whole big blue circle as the enzyme. So remember, the enzyme would be a long protein chain that's all folded up on itself, right, in some tertiary structure. And we're not drawing out that structure, we're just showing it as this blue blob here. But what we are showing in this overall picture is that triad, those important residues. So we have our aspartate, our histidine, and our serine. And if you look at that area shown in white, that is our active site. So it'll be somewhere near the surface of the enzyme. And that is where our substrate will come in, and somehow that reaction will be catalyzed. For chymotrypsin, a couple key features of this hydrophobic pocket, that's going to help orient our molecule. In this oxoanion hole, we're going to look at that. It's going to help us stabilize the intermediate. So when our molecule comes into the active site, it's going to orient itself such that the hydrophobic piece sits in that hydrophobic opening right there, that hydrophobic pocket. Notice that what that means with the way we have drawn our catalyst here is that even though we normally write our peptide change from N-terminal to C-terminal, in this picture, the N-terminal would be somewhere over to the right. Okay, because we can see here that we have this carbon here. Here was our carbonyl carbon, right? So we've got our alpha carbon, our carbonyl, and then our nitrogen from that phenylalanine in this case. So it comes in and it orients itself. That's the biggest key there. Notice that these three residues are all important, and we're going to look at why they're important. But another key thing is look at their numbers. You don't need to memorize those, but 57, 102, 195, these things are far apart in the primary structure, but because of the folding of the protein, they are in close proximity and all near that active site. A key thing with enzymes is the specificity, if I can say it, that is we want it to break the right bond, correct? So when we look, let's look right here at phenylalanine. It has this hydrophobic portion, and it's going to come in here and sit in this hydrophobic pocket. And then we have this area, what we call the oxyanion hole, but it's going to be this area that will stabilize a negative charge. And so this is going to orient such that the carbonyl from that phenylalanine sits down in that, okay? And we can see that. I should have copied the other picture over. Let's scroll back up here real quick. So here you can see that, right? that oxygen sitting down in here. Okay, here was our alpha carbon. And so it orients it in the right way. And then what we see is that the bonds that will be broken will always be on that carbonyl side. And this is interesting. So methionine has this fairly non-polar area that also sometimes in some versions will sit down in there. We didn't really talk about methionine being one of the ones for chymotrypsin. You don't need to worry about that. These bonds that are broken, call them the scissile bonds, a bond broken by an enzyme. If we look at that three-dimensional structure, the chymotrypsin has this opening near the surface, and we see our triad, are all sitting on the edge of that opening. Okay, so you can see if there's an opening, if we had a peptide that was going to come in to be reacted, it might come in right through there. And an interesting thing that's going to become important, we have looked at pKa's for these amino acids, but those pKa's can be manipulated and altered based on the overall bonding and the overall environment of the just of its location. And we're going to take a look at that because it turns out that pKa being altered is important in many of these mechanisms. All right, so here we go. We have, let's get oriented here. Okay, we're going to start right here in the middle on the left. Here, we're going to write start here. Let's do this in different colors. So what you see in the yellow is the overall enzyme. And we're just not showing all the specifics. But what we have drawn out are our three, the triad, right? So we have, if you look here, you've got your aspartate, you've got your histidine, and you have your serine. Okay, and we're showing those three specifically because they are going to be important to our overall mechanism. So then what we see happening right here is that we have some substrate that's now going to enter the active site. So that's what's happening, and we see it now up here at the top in the pink. Let's see if I got a pointer. I do not believe I know where the pointer is. So anyway, right here in the pink, we see that substrate. Okay. As that substrate comes in, we're going to see a nucleophilic attack from this oxygen right here on that carbon. So we see that nucleophilic attack. Now, to make that possible, it happens because the histidine is going to act as a base, and it's going to accept the proton right here. Whoops. I had to do that with a highlighter so we could see over it. Okay, it's going to accept that. But that's not what you would expect histidine to do at this with its normal pKa. But it is possible because if we look over here, the aspartate oxygen right here stabilizes this hydrogen from histidine with a hydrogen bond. And that stabilization changes the pKa and allows this nitrogen right here to accept that hydrogen. Okay, that makes that oxygen a very strong nucleophile that will attack the carbon. And as it does that, of course, then as it attacks the carbon, carbon would then have too many bonds. These electrons, right, come up here. Those electrons from the double bond move up to the oxygen. And so now move over to the next picture, and here's what we have. Okay, we now have histidine with that extra hydrogen, okay, right here, bound to it, and we have this anion. So we have those two things, and it turns out that this anion sits in what we're going to call a oxoanion hole, and it's stabilized, okay, by some of the hydrogens being attracted to some of the hydrogens from the backbone of the protein chain. We don't have to worry about what residues they came from or anything, but it stabilizes this transition state. And if you remember, as we stabilize the transition state, we're making this reaction happen more easily. So we form this tetrahedral intermediate because if you look at that carbon now, it has 4 bonds, okay, and we're looking at, let's highlight it, we're looking at this carbon right there. It has 4 bonds, so we have this tetrahedral intermediate. Then if we move on over to the next piece, let's see what's happening there. So we've talked about all these. I'm going to erase that so we can just look at the, whoops. Anyway, let's look at what is happening over here. So histidine is going to now turn around and act as an acid and give this hydrogen back to this, or give this hydrogen to the nitrogen. Okay, so what we see is we see that nitrogen on the histidine keeps the electrons. So these electrons stay with that nitrogen, and the hydrogen forms a bond with the nitrogen over here. Now those electrons come from this bond right here. So that bond breaks. Okay, there's our cis bond that is breaking. And when we look at this, there is a hydrogen bond. There's some hydrogen bonding right here. Okay, but we have a free molecule right here. This thing is not covalently bound to anything else. And because of that, so we broke that peptide bond, we have this free molecule that can now leave the active site, float out of the active site. But we are not back to our free enzyme because we have this acyl group right here. Okay, we have that group still bound to that serine. Okay, and hence we're going to call this the acyl enzyme. So it's our enzyme, but it's got this other group in there. That's going to prohibit other molecules from coming in. So we need to get rid of that if we're going to get our enzyme back. And so what we see is that water enters the picture. So we get this water molecule. It enters the active site. So as water enters the active site, it's going to act as a nucleophile. And that is promoted by histidine. So histidine is again going to accept a hydrogen. It's going to act as a base. So histidine's electrons are coming over here. We're accepting that hydrogen. So notice that when we get over here, we see that nitrogen-hydrogen bond. And that leaves oxygen a really strong nucleophile that's going to attack this carbonyl carbon right here. So if we move over here, we see we have that hydrogen bound to our histidine. And we again have a new tetrahedral intermediate. Okay, again, we have these other backbone hydrogens that stabilize that, make it lower energy. So if the transition state's lower energy, it's going to be easier for our molecule to make it over that transition state activation energy hill. Then what we see happens Okay. From here, we see that the hydrogen from the histidine is given back to that oxygen, or given to the oxygen from the serine. Okay, so the black oxygen there is the original oxygen from the serine hydroxyl group. The hydrogen came from our water. And when that happens, right, the nitrogen's keeping those electrons, and these electrons right here in this bond are coming over to form that bond with the hydrogen, which leaves this molecule free to exit. And look at that, we are back at our original molecule. Okay, there is a lot there. So we're going to do two things. We're going to look at the energy of those. So you might remember from Chem 301, 302, when we look at energy diagrams for mechanisms, we have hills and valleys. And in each of those valleys, here's an intermediate. So there was our original complex when the peptide first went into the active site. Here's that first tetrahedral intermediate. Here's that acyl intermediate. Here's that last tetrahedral. And then we're finally at products. Okay. Each of those hills is a transition state, right, to get over. So that's kind of what that looks like, just thinking back. And then I want to summarize because there was a lot. And I've got a blank copy of those pictures at the end of the slide so you can practice going through it and thinking about what's happening. But if we look at these, several key features. In the first step of the reaction, a proton is transferred from serine to histidine, okay? And this is important because it's just, or what I want to point out is that this is an example of acid-base catalysis, right? That aspartate oxygen right here stabilizes the histidine such that now histidine can act as a base and accept that proton. So we have an example of acid-base catalysis. Okay. And again, that was made possible by that hydrogen bonding. We see example of covalent catalysis. We saw new covalent bonds made and broken apart. That oxyanion hole, right, was a stabilizing feature. And so it's just important to remember that we want to stabilize those transition states to make their energy lower so that it's easier for the molecules to make it over that energy barrier. You can see here we have our oxyanion. We've got the hydrogen here and the hydrogen here from these other residues that were not part of our triad but are just separate residues, and those are stabilizing that. Okay, this is just another picture of that if it helps you to take a look at it. If it's confusing, skip it. And then a key thing is that we had to, for all this to work, we had to get the peptide into the active site, not just in there in any way, but in there and in the right orientation. And so that hydrophobic pocket really makes that happen. And that's what allows us to know which amino acids chymotrypsin will cleave, always on the carbonyl side of it. And there are other serine proteases that have pockets that fit other amino acids. All right, and here, as promised, is that chart if you want to try to step through it yourself. All right, that was a lot, so go step by step and take a look.